presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Good afternoon, everybody. I hope everyone's having a beautiful day. I apologize for the little bit of a late start today. I was hoping to get started a little earlier, but that's okay. That's okay. Welcome on. I see some lovely questions in the chat. I'll definitely chat about those. That's actually really interesting questions, especially about, there's a lovely question in the chat here about greedy algorithms, finding counterexamples. Yeah, we could definitely talk about that before we get into things here today. I think that's actually a great question, given that also that topic somewhat relates to the things I'm going to talk about here today anyways. So anyways, I hope you're having yourself a wonderful day. So just a couple things. I just sort of have to get my obligatory things out of the way. I got to tell you a little bit about some things. So the first thing is that, of course, if you enjoy what you're seeing, make sure you subscribe or follow and tell your friends to come on out, especially if you're interested in learning about computer science or other mathematical topics. The notes for today I'll have available on patreon.com/pagewizard. I have all sorts of rewards over there. And other things, of course, if you're welcome to leave any comments or anything like that. Of course, you have questions, I'm happy to answer those questions. One other remark I usually like to make is that whenever I'm kind of intermediate between kind of big parts of our lessons, the chat just sort of goes away like this. So if you're wondering, I could still see the chat. It's visible to me right here. And if, say, if you're, for example, on Twitch, I have text-to-speech enabled, so I do hear it in my earpiece. So I have both the chat here, and also I got my earpiece here. So I just wanted to mention that in case anybody's like, oh, well, where'd the chat go? It's like the chat is still, I could still see the chat. So wonderful, wonderful. So there's a lovely question in the chat. I thought I would address it because it actually is somewhat related to some of the topics we talk about here, especially about algorithms. That's kind of my wheelhouse. I really enjoy talking about algorithms here. It's a question about, if I understand the question correctly, it's about how to find a counterexample. In this case, it involves the study of, say, greedy algorithms. Now, for those that aren't acquainted with what a greedy algorithm is about, so let me just, before we get to specifically what a greedy algorithm is, let's just talk briefly about what an algorithm is in kind of broader terms. So the whole idea is that it gives you some problem. So imagine I'm trying to solve some problem. So this is my problem. I'm going to call it problem P. And in my problem, I have different problem instances. And each one of these instances, if I pull one out of this bubble here, I pull out one of them. And I ask the question of, okay, so if I want to solve problem P here, it's just a letter. It's nothing any special or anything like that. It's not the complexity class P or anything like that. It's just a name I've given this problem. So if I pick up one of these, what I know about this problem instance is that each one has some input. So it represents some input, which we would call the problem instance itself if we represent it. This would be represented as, say, the bits that you would use to represent this given dot here. And keep in mind, for interesting problems, it's almost always that you would think conceptually that there's an infinite number of these. That's why you can't just simply make a big lookup table with all the answers, okay? So the other thing is that each one of these problem instances also has a solution to it. Now, as I talked about in one of my previous lessons, when we talk about optimization problems, there's a broader concept of what it means for there to be a solution, which I'm going to talk about in a moment. So if we talk about an algorithm, so an algorithm is an unambiguous, that means, for example, if I pick up, I always like to analogize this with a sign I always see very often when I go for a little trip. It's something kind of like this. It's kind of like this. Imagine you see a sign on the side of the road and it says combat animal control or animal care or some other name. And it has some phone number or something right here. Now, if you've seen this sign over here, it says like you literally read it, it says combat animal control. Now, suppose that you've seen this and you're like, okay, so that's the name of the business, right? Now, you got to think about this from, say, the context of somebody that just has absolutely no idea how to read or interpret signs properly. They have to have some unique way of interpreting this sign. So if you read this like that, you might read this in a couple of different ways. You might read it as the name, combat animal control. That's one way you can interpret this sign. Or it's a sign instructing you to combat animal control. Maybe the animals that the animal control people are after decided, hey, look, we don't want the animal control people to push us around, okay? So call this number. The point is that when we want to solve problems, especially in the context of algorithms, we would like to have it so that when I communicate an algorithm to you, there's no way I can interpret it more than one different way, right? So this always depends on your audience and how formal you're going to be willing to be with it. So now that we have this idea of unambiguity, so that's the fun word of the day, unambiguity. It's not ambiguous, meaning there's more than one way I can interpret it. If I want to talk about an algorithm is just a finite, it's an unambiguous step-by-step procedure. I'm passing the buck on step-by-step procedure to another lesson. Maybe that'll happen in some future lesson. For those that are more acquainted, this might be in a Turing machine or something computationally equivalent to that. Step-by-step procedure that takes an input and produces output. That's a working definition that we can use to discuss this. So when I think about this, I imagine I have some algorithm. So here's my algorithm right here. Suppose this box represents the algorithm here. So for this algorithm to solve this problem, what it has to do is take each input as input, does some processing of some kind, and it produces output. Now this output might be returning a value, it might be outputting to the console, it might mean a lot of different things. The point is it produces output. And we would say that the algorithm solves problem P if I pick up any one of these problem instances and I look at this and I look at this and do they match? So if they're the same, then, and you must stress, it can't be just for some of the dots, it has to be for all of them. That's going to be really important to answer your question. So if I want to answer, hey, look, this correctly solves this problem, this algorithm, I need to have it so that for every one of the dots, when I give this input to the algorithm, it spits out output, it has to match the solution. Now, in the context of now, hopefully that is clear for everybody. Now, there's many different kinds of problems out there. Like there's function problems, there are just general problems like I've just described. There's ones that are more specialized or generalizations. One example is an optimization problem. In an optimization problem, instead of just having a solution, you have a collection of potential solutions. Some of them are, and keep in mind, all of them have to follow the constraints of your given problem formulation, but there's always specific ones that minimize or maximize some objective, the goal of your problem. This is what we call the objective function, and those that actually are able and capable of matching the best answer are what we call optimal solutions. So in those contexts, regardless, if we're trying to say we're exactly solving the problem, as I would say in that context, it has to still follow the same framework. So let's talk about how you can say that an algorithm works or doesn't work. So let's talk about it now in this context. And let me start with something a little bit more basic. Let's talk about, say, a sorting algorithm first. Let's start with, keep it simple. Let's talk about sorting. So suppose that I give you an array, or you just think of it as a list of numbers, or list of elements. As long as I have some way to order them from smallest to largest in some way, what we call comparable. So suppose I have, say, a bunch of numbers like this, 5, 2, 7, 1, 6, and 9. Now, if I wanted to get an answer for this problem instance, so imagine I give you the sorting problem where each one of these dots represents an array of some length, and each of them has some elements in there for me to sort. So the question is, okay, so how do I sort, I have to be able to sort any one of those types of arrays. So in this case, I have numbers in my arrays. So I would like to produce an answer. So for example, here for this instance, if I were to look for the answer here, it would be 1, 2, let's see, 5. Let's see, 1, 2, 5, 6, 7, 9, right? 5, 6, 7, 9. So this would be what the solution would look like. So the whole idea is that if I give you some algorithm that does sorting, it has to be able to pick off any one of these, which is, in a case of an example like sorting, that's going to be an array consisting of numbers. In this basic example, it may be other comparable elements. For a broader case, it'll be probably comparable elements. But the point is that your algorithm has to be able to do this, where every time I give you one of these, it's able to give me the answer. So now let's put this into the context of greedy algorithms. So now a greedy algorithm is a specific kind of algorithm based on the algorithmic technique called the greedy approach, or what we colloquially call a greedy algorithm approach. So there's all sorts of different ones out there, like you may know about divide and conquer. You may have heard of something called dynamic programming, possibly. There's a lot of different algorithm design techniques. So in a greedy algorithm, the whole idea works as follows. And the fun part is that this will be somewhat related to things we're going to talk about a little later. So in a greedy algorithm, so I gave you this idea that the algorithm just does some processing in here, right? So the whole idea is that the greedy algorithm is going to follow a basic structure as follows. So every one of these greedy algorithms, it follows the following idea. It has what you call a selection criterion or selection criteria, or what some people call a greedy choice. So I'll call it the selection criterion. And the selection criterion is what you use to decide what we call a locally optimal choice. So this would be the best choice you're going to make every single time. So you start off with no choices that you've made so far, and your goal is to keep applying the selection criterion such that every time you make a choice, whatever you're considered up to that point, it doesn't cause you to produce an answer that's going to lead to an infeasible answer at the end. But every time I do this, I'm going to apply this rule over and over again, which is always going to be the locally optimal choice. And that might mean a whole sorts of different things depending on what problem you're looking at. And I keep doing this until I end up with a feasible solution. So every time, for example, let me give you an example. Later on in this lesson, I'm going to talk about briefly about Prim's algorithm. Prim's algorithm actually has a characterization I'm going to prove for you later on, called the cut property. And the cut property, it works like this. So you imagine you give you some graph for just as an example. It doesn't have to be this sophisticated. But suppose I give you some graph and I have something we call a cut. So imagine I take some of these vertices and I have some that aren't a part of what I just circled. The edges that leave to go from inside the circle to the outside of the circle, they form what we call cut edges. And what you do in Prim's algorithm, which is one I'll talk about later, is you always pick the least weight edge that crosses that cut. And if you keep repeatedly doing this in the way Prim's algorithm sets out, you end up with what we call a minimum spanning tree. In fact, in that case, without knowing anything about how you can prove it, you just say it's a spanning tree based on the properties it is. But that's some better details that I'll talk about later. The point I'm getting at is that every time you just apply some basic rule that is just, hey, look, And keep in mind, the basic rule doesn't have to be very simple either. Just greedy algorithms tend to be very simple to implement. Let me give you an example. Say if we're talking about trying to give change to somebody. So say somebody wants to pay with something, but they need a certain amount of coins back based on certain sets of denominations. So like they have, say, have like a penny, a quarter, dime, nickel, things like this. And I would like to be able to reduce the number of coins I give the person. So naturally what you do is you try to start off with the largest denominations, you work your way down to the smallest denominations. Now, this doesn't work for all sets of denominations, but the greedy algorithm would just be quite simple. It would just always give the largest denomination such that you have not gone over the original amount, but you always pick the largest denomination to give first. That's what we call the selection criterion for the, say, for example, this so-called coin change problem. So in that case, you can see how every time I make a choice and it leads me to an answer, and the answer doesn't invalidate any of the rules of that optimization problem. So that's the other characteristic of one of these things. So some people call this a greedy choice. And in a greedy algorithm context, if I want to ever show you that this thing, in fact, this greedy algorithm I maybe posit to you actually works, I prove something called the greedy choice property. So this is often called the greedy choice property. It doesn't have to be called this. It's just a name that algorithm people sort of just gave this as a general characterization. That means essentially the following, and that each problem has their own way of characterizing this whenever you are able to do this. So if you have what we call the greedy choice property, you can guarantee that this selection criterion will lead you to which is obviously a locally optimal choice. It gives me a globally optimal choice. So that's the nice basic way I'll describe it to you. So locally optimal. So making locally optimal choices means that you end up with a globally optimal answer at the end. Now to answer your question, so let's go back to my original picture I have over here. So you say how, oh, the greedy, like how do I know the algorithm doesn't work? So let's look at this picture and then I'll kind of give you some tips involving specifically greedy algorithms, okay? So now to know that an algorithm is in fact going to solve a problem means I can pick up any one of these dots, and keep in mind there can be many, there could be infinitely many of them. So many that I couldn't even imagine how big those arrays would be, like say like the sorting problem. But if we're talking about any one problem, the idea is that I pick up one of these guys, I feed it to the algorithm, and it produces output. And I check if it matches the solution. So if that happens always, no matter which dot I pick up, that means the algorithm solves the problem, right? So the question is, let's flip the logic here. So to say that the algorithm solves the problem means that for every, and suppose one of these is called x, for every x in this problem, p, this is just a name I gave it. It could be called k, it could be called whatever. For every x in p, the algorithm produces correct output. That's what it says. That's what it means to say I have an algorithm that solves the problem. It means for every one of the instances, the algorithm produces correct output. So now let's take this idea and play with the idea that the algorithm doesn't actually solve the problem then. So this means problem solved, but what does it mean if I don't do this? So that means that I'm able to pick up one of these dots, one of these problem instances, that's what these are called, just to be very clear. That's a problem instance. A problem instance. I pick up one of them. And now to answer your question, the first part, I pick up one of these. And then I look at and give it to the algorithm. So I give it over to the algorithm. And what happens when I check the output in the solution? They don't match. They don't match. That means all you need to show that an algorithm doesn't work is to produce a counterexample as you'd suggested. So that just simply means that, so if this means to solve a problem, it means to not solve the problem means that there exists an x in the problem where the algorithm does not produce correct output. And you might ask, Dan, how do you double check this? Well, one, this is a logical negation of this statement. Two is you always just look at this question and you say, okay, well, if this means solving it, okay, what kind of game can I play with you to tell you that it's not actually solving it? Well, I just had to pick up one of those and show you that it doesn't work. So now let's bring this into the context of the greedy algorithms, because that's really, I think that's the heart of your question. At least correct me if I'm wrong, okay? So this part that I really want to talk about now is the greedy part. So we know what it means to show that there's a counterexample. So we would call this instance, so any one of these, you can call a counterexample by any other, yes, indeed. Finding counterexamples is sometimes not very easy. And it really, I will give you my general advice when it comes to dealing with these guys. Because most certainly, it's, as you probably could guess, it's like, oh, well, how do you do it? Well, the first, the kind of broader answer I would give you is you just find one of them, but it requires you to first understand what the algorithm does. Because the whole idea is you're trying to outsmart the algorithm. So you pick off one of these dots, but you want to make sure it's one that causes this inconsistency between, in your case, if we're talking about an optimization problem, that it doesn't produce an optimal solution. So you got to think carefully about what the algorithm actually does. So let me give you, I think maybe I'll present this in a somewhat interesting way. Actually, I'll give you one concrete example of how you might go about this. But let's talk about how you would apply it here. So we know that the greedy algorithm always applies this rule over and over again. So you got to think about it in terms of trying to create a counterexample. Try to find something that outsmarts this selection every single time. So usually the way I like to think about it is you're like outsmarting the algorithm by finding something that will be ahead of time producing an optimal answer that would not actually be there. So that sounds a little bit weird at first, but let me give you an example of what I mean. So instead of talking about, say, minimum spanning trees, I'm going to talk briefly about shortest paths. Let's talk about shortest paths. Because that's another kind of hallmark case where you study greedy algorithms. In fact, it has some of the theory relates to some things I'll talk about today, but most certainly that's more we're going to talk about some other stuff too, but one common thing that does actually come up, and this is a very common exercise, by the way, is, say, for example, now I'm not sure if you've ever heard of Dijkstra's algorithm before. It's another greedy algorithm that's out there. Dijkstra's algorithm. So in Dijkstra's algorithm, it solves what we call the single source shortest path problem in the context that classically, where the edge weights of your weighted graph are what we call non-negative, meaning that they're not allowed to be negative in that context. So there are other shortest path algorithms that are able to handle negative edge weights, but the thing is they have no ability to really do much more once you identify what we call a negative weight cycle. An algorithm like that is such as Bellman and Ford, or what you might know as Bellman-Ford. Either way, this is something interesting. So some people ask me, Dan, suppose I wanted to solve the problem of the single source shortest path problem. That means that I imagine I give you a graph, maybe something like that I have over there. I designate a source or start vertex, and I would like to find the shortest path from this vertex to any other vertex in the graph, where I'm going to assume that there's edge weights that represent the distances. So this algorithm, you can show, works when all of the edge weights are non-negative. So it's a very classic formulation of this problem. But what if I allow the edge weights to be negative? So So the question is, suppose I consider a generalization of the single source shortest path problem where the edge weights are negative potentially. So does it work with negative edge weights? And I'm going to kind of walk you through this process of kind of outsmarting the algorithm, okay? So that's what we're going to try to do here. And at the heart of how we're going to do this is what we call the edge relaxation. Now, you may or may not have heard of this concept before, but in an edge relaxation, the way it works is that you have it where every time you pick your next vertex, it's going to be a part of extending some shortest path into your shortest path tree, for example. When you do this, every time you update along all the incident, like say for example, for just hypothetical purpose, I didn't put edge weights or anything on here. When I do this, all the incident edges, I look at these and see if there's a potential for any one of the other vertices to get their distances updated, meaning that there's a closer one. And this is maintained through what we call the edge relaxation mechanism, or just edge relaxation for short. So the idea is that if I give you the original distance from here to there, the idea is that if I could find a shorter distance to get to this one, or this one, I want to update those distances because the way Dijkstra's algorithm works, and I'll give you now the selection criteria, is you always pick the next closest vertex to the source. That's how this works with Dijkstra. So now, the mechanism of the edge relaxation presumes the fact that whenever you take a step towards the next vertex, it's always a step that's either where you currently are, or one step forward, or two steps forward, or more. This is actually how Dijkstra actually uses the edge relaxation mechanism. That's actually why, say if you ever study something, say Bellman-Ford, it actually uses edge relaxations many, many times, because the only way Dijkstra is able to do this is that it always presumes that the way you select or include the next extension to your shortest path tree, it's always that you went at least some distance that isn't going to make you go backwards, okay? So let's think about this now. So I have some idea here where I always pick the next closest vertex, but the way that Dijkstra's algorithm does this by updating is what we call this edge relaxation. It always presumes that I always go, either I stay in the same spot or I walk some distance forwards, okay? So let's kind of look at this, and I'm going to give you kind of an idea of how I might come about a counterexample for this case to show you that Dijkstra's algorithm can't be used to solve this broader problem. So that doesn't mean that you have to be very careful, because remember our picture that we had, had all those problem instances. There will be some instances where the negative edge weights do actually work. We just can't guarantee it might work for all of them, okay? That means we can't solve that problem because there's some mismatches that will happen. So anyway, so imagine I have a vertex here. I'm going to have 3 vertices. So I'm going to consider something that looks like a triangle here. So I like to show this example because it just sort of gives you an idea of like, don't make your counterexamples too big. Just think about what the algorithm does. So in this case, it's a greedy algorithm. So Dijkstra always pick the one that's the next closest vertex to extend that shortest path. So what I'm going to do is we're going to try a couple of things, and we'll see what we can do to figure this out, okay? So first, I'm going to make this let's make it say -3. So we're going to kind of walk through this process together. So I'm going to make it so that this edge weight is -3. And then I'm going to make it so that, let's make this a -10. And let's make this a 1. Now you might ask how I picked those. I just made them up. Like I didn't really give them much thought, except for the following idea. Remember, I told you that we always extend the shortest path tree by finding the next closest vertex to the source. And remember, it might be through several vertices. So the question is, now let me give these names. I'll call this one A. I'll call that one B. So now the question is, okay, so in Dijkstra's algorithm, how would I extend this shortest path tree? Well, would I pick this edge to go across to include B? Or would I use A? Which one? Which one? So it always picks the closest vertex to the source, the next closest one. So just here, look at this. So notice that this edge right here is -3. It's -3 versus 1. -3 is less, right? So that means that I would include this edge. So to extend my shortest path tree to include A. That's what I would do first. However, let's think about this. So if I'm doing the edge relaxation, it says that if I were to do this, I would update the distance. So right now, if I were to look at this, I would, because remember, I would first start off with including this, then I would update the distances. The current distance for this vertex is 1. This one is -3. So what it would do is it would check, okay, my distance is -3. I'm going to check if -3 plus the distance of this is in fact going to be less than what's currently right here. So -3, -10, that's -13, right? Yeah, an edge relaxation happens here, right? So they'll update this. So now you get -13. And then naturally you would go through this again, right? You would say, okay, well, which one is the one that's closest to the source? Well, this is -13, so I would include this one next, right? Now, so that would be, for example, the shortest path tree I would get here, right? And this indeed gives you one that actually works, right? So let's see what we could do to break this example. So let's take a look and see what we could do here. So the first thing is I would like to have it so that it picks as early on as possible a shortest distance that makes it so that I don't want it to go this way. Instead, I want to make it so that it forces it to take this edge and that edge, but not this one. So watch this. Yeah, you're getting really close here. So what? You're getting very close. So watch this. So what I'm going to do is I'm going to maybe make this. Let's make this something that. Let's make it so that this is slightly bigger. Then we will make this, let's try maybe that maybe. Let's see, I'm just trying to think of some ideas here. I'm just trying to come up with this with you together here. So let's walk through this process again. I'm just gonna see if this does anything interesting for us. Because first the distance from S to S is 0. And let's go through the same process again. Now, you'll notice that this time it should pick this bottom one because -5 is smaller than -3. So the distance here will be updated. Well, keep in mind these would be updated to -3 and -5. So let's see here. So now we got -5 here. And then you ask, okay, so we got the distance from, because that's smaller, right? That's the smallest one. That's closer to, B is closer to S than A is. So let's try something here to make this a little bit more fancy-pantsy. Let's see. So it's saying that I should try to get it so that I have -5, and then notice that -5, this current distance, plus -1 is a smaller distance. So notice that I'm not really getting that much further here anyway. But notice that now I'm picking the -6, so that means I'm going to probably want to go to here first. As opposed to going through this edge, I would take this one. Now, keep in mind that that still doesn't get us exactly what we want, but you'll notice that now I have some control over which way that's going to go. Do you see that? So like now I have some idea of how I can try to force the graph to pick something. So in this case, which vertex to go with first. So what I would like to have happen is I would like to make it so that it prohibitively picks this one, but there's actually a shortest path that's even closer. So let's try, I'm trying to think of some ideas here. So I usually have this idea off the top of my head, but I'll give you a moment to think about it. Let me just check something over here. I always like to make sure things are going okay here. Because I swear because I was actually thinking about this the other day. Okay. Let's now that you see that I'm using negative weights, let's try to do something with positive weights. You see how negative weights, I have some control over how I want to do this, but what I want to do is trick the algorithm to pick one that is going to lead me to a potentially longer distance, okay? So let's pick another source here. And I'm just thinking about some couple things here. Don't mind me, I'm just off the screen at the moment. I'm just checking one small detail here. I just want to make sure that I give you the right tip to think about this. Okay, so let's think here. Because I want to give you a nice kind of general formulation for this. Because I'm sort of just doing this on the spot, which makes this a lot more fun. Because one other thing I also want to point out about Dijkstra, by the way, is that, remember, when you commit to including a vertex, you never reconsider it again. That's another element of this. So it's because every time when you include another vertex, and some people call this the blob or a cloud or something, or a set of vertices, that's really what it is, of the vertices that make the parts of your shortest path tree. Yeah, Kleinberg and Tardos is an excellent book. Excellent book. I like that book because it kind of walks you through the thinking process, but I definitely wouldn't recommend it for beginners. It's still a great book, though. I know that I use something, well, I've used it in the past for teaching courses. Yeah, no, it's an interesting book. It got a lot of the fundamentals around this kind of stuff. I like that it gives you kind of some thinking process around this. I'm just trying to find my one fun example here that I had. Because I made a really nice characterization for this. Let me just take a quick peek here. I just want to double check this. Like I said, I'm just having a little bit of fun here with you guys. Well, before we get to kind of the... this is what I was looking for. Yes, I found it. I found it. Okay. It's because, remember, we want to trick the algorithm. So now let's talk about this. Let's talk about this. So what I would like to do is I want to try now to introduce positive weights into this. Now, you might say, Dan, how exactly are we going to do this? So let's think about what would happen instead if I do this. And let's make it so that this one right here is a little bit bigger, but not too big. Let's go with something like this. And I think just to really hammer this in, I'm going to make this into a 4. I can keep it a 5, I think, but let's kind of go through this process again. And we're going to start off here again at S, and let's see what happens. So first, I pick this, I include A, and then what I do is I consider what we can do from there. So I include this one. The distance here was 3. Keep in mind, at that time, distance here would have been 4. And then what I do is I'm going to make it so that when I pick this, I'm going to now go through my incident edges, perform the edge relaxations as necessary. Keep in mind, to get this was an edge relaxation, right? But I'm just trying to think about this because we need to make it so that it forces it to pick the wrong way, okay? So I would like to make it so that, I think I have an idea. I think we got this. I think we got it this time. So let's see. So next what's going to happen is it's going to update the D value here from 3. So it's going to be 4, sorry. And so it's going to take 3 plus say, let's think about, let's go with, we've got -4. I'm trying to think if that's the correct value we want here, because we want to try to bring this down a little bit. But you remember, I took this edge, so I've committed myself to this one. So that means I'm going to have to pick a pathway here. So if I do this, I'm just trying to think here. I totally have this on the tip of my tongue here at the moment. So let's see. I just trying to, I want to make sure I craft this properly for you. So, because there's a lot of ways I can come up with this for you. So let's see here. Just trying to think here, because you would have C plus, just having a bit of thought here. Because I swear, either way, my main point I'm getting at is I would like to make it so that it kind of forces you to pick another vertex here. So I'm having a bit of a brain fart at the moment, as you probably could guess. I'm usually very good with this one. So we have it where we have the 3, and then I do edge relaxations. Yeah, because it should be, just to be very clear, it should be that I have it where it goes from S to A, which that will be something that's larger than 0, indeed. Then, yeah, that's right. That's right. I'm having such a funny time at the moment. So what I'm going to do is we're going to try to see what we can do here. So if I pick that one, I would like to make it so that this is a, let's make this into a, let's make it minus, I would like to make it so it's big enough, because the whole idea here is we want to force it to go this way, but it's actually supposed to go this way. That's what I'm trying to get out of this. So I want to make it so it goes this way as opposed to this way, but I want it so that it goes like this, when the algorithm is going to go like this. So I must stress, the reason why I'm doing this with you is that I really want you to kind of like see how we could think about how to outsmart the algorithm in this case. Because the negative edge weight, I would like to put it right here so that I pick it so that it goes one direction as opposed to another direction. But it's going to play really dumb because it doesn't know what to do. So we're trying to get ahead of the algorithm. Now, you might know of that phrase from Kleinberg and Tardos. They always talk about being ahead of the algorithm. So the correctness always has to do with what we call an exchange argument. You may have seen that in that book. And that's a very powerful way of arguing the correctness of greedy algorithms. So the whole idea is that we would like to be able to try to find a way to take advantage of the fact that we could trap the algorithm into making a really bad choice by forcing it to make some choices that make sense at first, possibly. But then usually the idea is you try to like fudge it and make it so it does something really bad. But it's all going to be based on the selection criterion. So what I would like to do is I would like to make it so that it does something kind of like this. So I'm just having a little bit of fun here with you, because there's a lot of fun ways you can think about this. Just having a bit of a brain fart at the moment. I probably just have it here. It's just that, like I said, I'm having a little bit of fun with this. I'm just having a bit of a brain fart at the moment here. I know I just have it just sitting right there. I'm just having a bit of a fun time. Okay. Let's see here. I'm just trying to think off the top of my head here. Just please be patient with me. I want to explain this properly. So, but the whole idea, hopefully you're seeing what I'm talking about. We're trying to get it so that it fudges with this so that it creates a shorter path. Yeah, I think you had it there. Yeah, you said -2. I think that's what we should try to do here. Yeah, I think you might be right here. Because we would like to make it so that if we can get it to be shorter, yeah, we want it so it's shorter this way, but I also want to make it so it does something that will fail to find it. So let's think about this. Because let's think here. Because I find the closest vertex, but the thing is the way the edge relaxation works. But the whole idea is that we don't want the negative weight to appear on the shortest path. That's kind of the big trick here. If we get the -1 to pop into the shortest path, we're going to have some problems sometimes. Yeah, I'm pretty sure we got it. Either way, my whole point is I definitely will prepare a nice little lesson on this specific one in the future. But the whole idea is that you want to make it so that this one is smaller than this one. And then you want to make this one the negative version of this one. And I think that that'll be enough to get it to work. But the whole trick here is just that you want to make it so that you can try to play around with what the decision's being made. I think -2 should cut it, I think. Because the whole idea here is that this distance will be less than 3, right? This whole distance is less than 3. But anyways, hopefully this gives you some ideas. Another example I can give you. Actually, I'll give you another example. This one I'm a lot more cozy giving it to you. Because it's, like I said, it's a little bit of a weird day on my end over here. So that's Dijkstra. That's one example. Let me talk about Knapsack. Let's talk about 0 on Knapsack. And why you might not want to use a greedy algorithm here. And except for very narrow circumstances. For example, you might know of a nice classic problem for the greedy approach is for the fractional knapsack problem. That's where you have the items that can be fractionally placed into the knapsack. So you can take half of an item and so on. So let's talk about this. So I'm going to walk you through kind of a very similar process. The whole idea is that I didn't want to necessarily get the counterexamples to show you that by making choices, you could fudge around with what you're trying to force the algorithm to do something that's really dumb. That's what it, because remember, the greedy approach doesn't always work. That's the whole point, is that always picking a locally awful choice doesn't lead you always to the best answer. It's an effective one, especially if you think about it from a heuristic standpoint, but definitely not for every problem. Unless you're doing something very specific for your selection criterion. Each one has a different characterization for a problem. But let's think about 0 and knapsack now. Now, as I already told you, you could solve a version of this problem called the fractional knapsack using a greedy algorithm. So this is where you're allowed. So let me give you the whole flavor of this. So we have the fractional knapsack problem. The idea is that you're given some knapsack. So you have a knapsack. Let me get my knapsack. Yeah, dynamic programming is one of the classic ways of solving the 0 knapsack problem. Exactly. So if we're talking about, in this case, for the greedy approach, if you want to talk about how we can show that this greedy approach doesn't work for knapsack, let me show you. So just to give you a recap, just in case anybody's watching this, we have a knapsack. It has a capacity. I'm going to call it capital W. There's also going to be a set of items that I get. Each one has a profit and a weight. And my goal is to maximize the total profit. So I want to put them all in here such that the following constraint holds, such that the total weight is at most capital W. This is a guy's classic packing problem. Yeah, you can use, so keep in mind, remember the burden of the claim. So the only kind of proof that's sufficient, but you don't actually, let me be a bit careful about this. If you wanted to show that an algorithm is incorrect, all you have to do is present a counterexample. You don't have to show that it doesn't work for every instance. All you need to do is show it for one instance it doesn't work. So what I want to do, so if we're talking about fractional knapsack, however, normally the way you use the exchange argument is that when you come up with an exchange argument, it gives you a characterization for this, what we call the greedy choice property, where I can take and always swap a part of the answer based on the selection criterion to either improve or maintain the same value for the objective function. That's how an exchange argument works. And then the idea is when you prove the algorithm's correctness, you suppose that the algorithm, for example, doesn't, and this is a very common way of going about it, is you would presume that the algorithm doesn't actually produce what you're claiming. So say if we're talking about like the minimum spanning tree problem, you would suppose that the algorithm doesn't produce a minimum spanning tree. Or for example, if we're talking about, say, fractional knapsack, you'd suppose that it produces a knapsack. Keep in mind, you would have to prove that it produces a knapsack with capacity at most W first. That's one part of the correctness of the algorithm. Then what you would do is you would sit there and say, hey, okay, I want to show you, I'm going to assume for the sake of a contradiction that the profit is not maximal, meaning that there does exist a better knapsack. So what I do is I just simply pick up the characterization I get from over here. And what I do is I show you that because the knapsack has to differ by at least one item, otherwise it would be the same, right? I have to differ by at least one item. Yes. So if I have one item that differs, I look at that item and then I try to observe some property it may have, compared to the one that would be otherwise not in the knapsack under the assumption. Then what you do is you pick up your exchange, you pick up this, and then you say, hey, look, if they don't match, there's some property that the algorithm has. It always does blank. It does something. For example, in the greedy algorithm for fractional knapsack, you always pick the next profitable item by profit over weight, right? So that's a property you could pick up and say, hey, look, this is what the algorithm would pick for this item. So normally in the way the proof goes for fractional knapsack, you would list out the items based on the choices that are made at that time, and you look for the first disagreement that happens. So where your hypothetical optimal that our algorithm didn't obtain, you look at that first disagreement that happens. And then you say, okay, those two differ. So why did that differ? So you just look at, okay, so the algorithm at that time had to have picked this. And now, naturally, you could pick this up and do where now I must stress that there's a way of viewing this with induction or contradiction. So induction, you'd induct on the number of items. In contradiction, what you do is you look for the disagreement, and then you ask the question, okay, my algorithm always picks the most profitable by weight, right? So then you look at that disagreement and you say, okay, well, that means that this one had to have a higher profit, even though I would have picked one that would have been better, more profitable, right? By weight. So then what you do is you try to come up with a better one, and that's how the proof for the exchange argument, I'm pretty sure Kleinberg and Tardos actually has a proof like this in the book, if my memory serves me correctly. I have it on my shelf over there. But what you do is you just employ the property, the characterization that you get for this guy. So that exchange argument is what you use to say, well, look, this says blank about how I pick the items. And that means that so-and-so, meaning that I can always obtain one where the knapsack's profit is either the same or better. So what I do is to improve my answer, I swap those two items. And then I go to the next disagreed item. And then I ask the same question. And I can keep inductively applying this argument over and over again. So I just keep repeatedly doing this. And the whole idea is that once you're done, you look at it like, hey, look, my hypothetical answer that was not as good is actually just as good as the optimal one. And then you're just saying, hey, look, that's a contradiction, right? Because I assumed that my answer wasn't optimal, right? And so that if my memory serves me correctly, that's how the proof goes, at least with Kleinberg and Tardos, the way they have it set up. But yeah, so that's sort of an aside. Let's talk about how, if you picked up the greedy algorithm for this, why it doesn't work for this. So I thought this would be another good example. Just to kind of walk you through this process of coming up with a counter example. Now, I will mention that I usually like to throw this type of problem on exercises. So if, say, a student has ever taken a university course with me before, like in the past, I like to throw this on homework problems because it's a fun one, but I like to go a little extra further with it. So I'll give you kind of the basic version of this. So you can go even further with this to show you that the greedy algorithm is actually really terrible if you just use it naively on zero knapsack. So here's one way you could go about this. So suppose that I gave you the algorithm that we had for the greedy algorithm for fractional knapsack. And I want to use it for zero on knapsack. So the idea in that algorithm is that you always take the largest chunk of the item you can until the knapsack becomes enabled to fit a whole item, and then you'd shove in whatever's left. Now, the way you would modify this is you would just simply, whenever you take an entire item, you do that anyways with zero knapsack, right? So whenever you have it when you can't fit the whole item, you consider the next item. And then you consider the next item until you can keep filling the knapsack. So the idea is that you never put a fractional part in, instead you put a whole thing in. And you just do this, you consider this for all the items. So that's the only tweak I'm making to the algorithm. So it's still a greedy algorithm, it's just not going to be correct. So I want to justify that to you. So naturally, if I wanted to prove to somebody that the algorithm is incorrect, I just present you a counterexample. Now, I must stress that usually the best kinds of counterexamples are the ones that characterize whole sets of instances. You know when I had all those dots at the beginning? Oh no, wonderful. The whole characterization here is I would like to have some way of identifying a whole bunch of the dots and telling you not just one counterexample exists, but I could characterize it as just a whole bunch of possibilities that could happen. And these might characterize a whole subset of all the instances. But all you really need, logically speaking, is just one. But we'll try to do better and try to come up with a whole bunch of instances. But I just need one. But the reason why I suggest this is that sometimes, just to play devil's advocate with you, suppose that I have some example. Suppose I have, like, just point out one counterexample. Somebody could argue to you is like, okay, well, there's just this one example where it goes wrong. What else could be wrong about it? And then they might tell you, okay, well, I could just use it for all these other instances, right? Well, like, if you could show that person that there's an infinite number of these counterexamples, they would either have to program that directly in and say, hey, look, for all those cases, we can't use it. Now, I must stress that you would not want to recommend giving somebody an incorrect algorithm, but I'm just giving this as a devil's advocate position because there are people out there, I'm not joking, that will say, oh, well, this one doesn't work, so we'll just kind of work around it, okay? I would not recommend doing that as an algorithms person myself. I would not recommend that, but most certainly if you had a way of solving those instances that don't work really well, that's perfectly decent. Just the thing is, you still have to show that all the other instances still work correctly with your algorithm. So let's talk about this. So remember the tips I gave you earlier. First, try to think simple about the instances you're creating. Second, make sure you understand carefully what the algorithm is doing. So one thing that we can exploit about 0 Knapsack versus Fractional Knapsack is that we have to take whole items as opposed to parts of items. So I would like to try to exploit this fact. Likewise, I would like to be able to exploit the fact that we have a cap on the sides of the knapsack. So what I'm going to do is I'm going to try to make it so that I have a very small number of items, but I want to try to make it so it forces the selection of one item over another item. But the thing is, the other item might be more profitable, but by profit per weight, in the 0 Knapsack sake, it would not be. So here is an idea. So I'm just going to start off with 2 items. Keep in mind, you can have more items. I just suggest having 2 to start off with, because one isn't very, yes, yeah, oh yeah, no, that's a scenario that exactly, yeah, I know that happens there, but I mostly was talking about just generally, yes, is that they will just drill down, they just keep modifying the algorithm, exactly, yeah. So they just want to get the test to pass. I remember some years back, I did one of those ACM competitions. It was some years back, like years ago. I remember being in the room with some people like, oh, I just need the test to pass. I'm like, okay, well, like, are we doing it correctly though? But that's a whole other side discussion. My point is that we want to have it. So if I have 2 items, what I would like to do is make it so that one item has a very high, I want 2 items. I want one where it has a very high profit per weight, a very high profit per weight, and the other one I want to be more profitable, but has less profit per weight. Do you see why I might want to have 2 items like this? Because the greedy algorithm always is going to pick this one. Item number, if I number these, it'd be like item 1, and this is item 2. I would like to make it so it picks this one over this one. Yeah, no, that's a good way of going about it. You want to make sure, like, usually my advice, especially the computer science students, is take a step back first, understand what you're trying to solve. I at first because I oftentimes teach data structures and algorithms courses and a lot of analysis of algorithms classes, so sometimes it's a bit of a culture shock for some students where like, hey, have you tried doing this on paper? And sometimes they haven't thought about doing that for some reason. It happens. Just take out a piece of paper. Try to convince yourself that the algorithm is in fact correct. The best way to do that is formally proving it, but you got to ask yourself, does it make sense first? So try it out a little bit, see if it makes sense. Convince yourself, and then put that legwork in. And the other tip I usually give, especially those that are interested in practice, is try to focus on things that work first, then, and I must stress, when I say work, I mean they're correct, and then if you can't find things that are already known to be correct, then take those steps to do all that extra work. Sometimes it's not best to reinvent the wheel. That's what I'm trying to get at. But my point is that we have two items. I would like to make it so that, because remember, the selection criterion in this case is to pick the one with the most profit per weight, right? So the whole idea is I want it so that the instance, the counterexample, picks item 1, but it can't pick item 2. So the optimal solution will be the one that's number 2 only, and the one that the greedy algorithm picks is item 1. So we got to make it so that the ratio is it's much bigger. But I want to make it so that the profit of the other item is a bit bigger, so that you can have it where when you put one of them in the knapsack, it can't fit the other one too. So I don't know, I'll call this one item 1. So I have item 1 and item 2. So each one has their own profit or weight. So let's imagine I have a profit. So profit 1, weight 1, profit 2, weight 2. And I would like to assign these accordingly. So remember, I have a knapsack capacity of capital W. So I know if I make it so that the ratio between these two things is big, but it needs to be bigger than the one for item 2. So you might think to yourself, okay, well, does that mean like the profit has to be like really, really big? Not really, no. It's just the ratio between the two has to be big. So there's a lot of ways I can characterize this. So if I remember, the goal is to just make it so the profit per weight is larger. So if I make it say, let's just start with something pretty basic. Right now, I'm just going to make them so that their profits and weights are both 1 and capital W. So this would make no difference which one you pick, right? That's where I'm just going to start off with. I just want to start off with something basic. So notice that you only could put one of these two in the knapsack, right? So next, naturally, I would like to make it so that the ratio between these two things, so that's the other part of this. I want to make it so it picks 1 but doesn't pick 2. So next, naturally, I would like to make it so that the profit is a bit bigger per ratio. Now, it doesn't really need to be that one of these has to be W, right? As long as one of them is W, we're okay. So if I make, say, one of these items, say, have weight, actually, maybe we'll keep this one. Maybe we'll make it so that the item 1, the one with the very high profit per weight, has weight 1. And then what I can do is something like this. I don't know, I can just, let's try doing something like this. Let's see. Let's make it so that this is, say, I don't know, I'm just having a little bit of fun here with you. So let's make it so that this profit is a bit bigger. Well, let's start off with W. Let's see what happens if I put W here. So I must stress that the knapsack capacity, I'm just going to presume it's a positive integer, but okay, just to play it safe, we'll call it like W plus 1. We'll make it so the profit's W plus 1. So now notice that item 1 has W plus 1 over 1 for its profit over weight. Item 2 right now has profit of of 1, but you only could put one of these two items in. Right now, this one needs to be more profitable. So let's make this one's profit bigger, but not more than W plus 1, okay? Because that's what the ratio is there. So let's make it so that maybe this is W plus 2, for example. So notice if I take the ratio of profit over weight for the first item, now it's W plus 1 for that. And this is just slightly bigger than 1, right? Now, you can see how we can play around with this, right? Do you see what I mean? Like, so I'm trying to show you how when you have a greedy algorithm, what we want to do is try to outsmart it by trying to take advantage of the way it picks the items every single time. So in this case, like with Knapsack. So I'm just trying to give you some ideas of how you might approach this. So in this case, if you were to pick, like keep in mind, it would sort the items from profit per weight, and it would pick item 1 first. So notice here that it'll pick that one first, but it will not be able to pick this one because it matches the capacity here. It won't be able to fit. But now notice you have a counterexample, right? Do you see how this is a counterexample to a greedy algorithm? Like if I adapted the fractional knapsack greedy algorithm for 0 on knapsack. So now I given you a nice, hey, no worries. No. I'm happy to do this. I was actually thinking about something else to throw into the lesson too. So I'm happy to do this. So please, I'm happy to go through these kind of things. But now, here's the cool part about this. So I want to mention this to you. You can take this idea and go even further with it. So you could say, okay, well, Dan, that profit for item 2 is a bit higher than the one that's over for item 1, right? Well, you can actually make this really bad. So there's actually and I'll let you think about this. This is what I meant by the exercise I like to put students through. Is think about how you can make it so that the greedy algorithm always takes and makes answers that are, so for any one constant that is greater than 2, I believe, I think it's 2, that whenever, it's always going to be C times worse than the optimal. So what you could do, and if you assume C is a constant, you just put C in places like where I have capital W here, with the exception of this one right here. Just keep that one right there. If you play around with this constant C, there's a way you could fudge around with this such that whenever you use this greedy approach on 0 on knapsack, it will produce arbitrarily bad answers. So this is what I mean by characterizing a large class of instances. So in these situations, the greedy approach is really bad for 0 on knapsack. There are situations where the 0 on knapsack is more effective with the greedy approach, but it's not ones like this. You would have to do a little bit more workery with this kind of stuff. I made up a word just now. But the point is that, do you see what I mean? Like, this is what I mean by trying to come up with a helpful counterexamples. You look at what the choice that the greedy algorithm always makes is. And what you do is you try to craft the instance so that it picks bad answers. But the thing is, to pick those bad answers, you have to understand what the algorithm's doing. In this case, I came up with this intuition because of how the items get picked by the greedy algorithm. Just like if I considered another algorithm, if it always tells me to pick something first, what I would do is I would want it to pick something first that's really bad. Does that make sense? So like in this case, I want to make it so that it takes advantage of the fact that it picks the most profit per weight item, right? If I do that, it always pick this one, but not that one, even though that one's more profitable. And keep in mind, the way I crafted this is that I made it so that you can't have both. Just like in the example I was trying to get through with Dijkstra, I definitely want to revisit that one at some point here on the channel, just to kind of go through a proper counterexample with that one. It's a very common one to run into. I will properly go through that one at some point. I just wanted to spitball and think about some ways of going about this with you. But hopefully that helps a little bit with your question. But yeah, no, like you could do this type of thing with any one greedy algorithm because they all have this sort of similar structure to them. Is that just think about how you can get ahead of the greedy algorithm using the phrasing of Kleinberg and Tardos. So you want to try to get ahead of the algorithm by showing that you could basically send it on a pathway of making really bad choices that eventually culminate in an optimally bad choice. It doesn't have to be a really bad solution. It just has to be one that doesn't produce an optimal one. So in this case, for example, you can craft this one. You could play around with it a little bit more. You can end up with really bad answers for the greedy algorithm. This is actually one of the reasons why you might think about using dynamic programming, like you had mentioned, the nice classic one for Zero and Knapsack. In that case, one thing I will mention, just as a fun aside, if we've never heard about this, is that and the reason why I brought this up is that a lot of optimization problems, they have what we describe as approximation algorithms. Kleinberg and Tardos, I believe, has a chapter or a part in one of the last chapters about this topic. It's one actually I do research in. I'm in that area. So the big trick is even if you can get bad answers here, are there ways you can still get reasonably good ones that you can actually sit down and form a proof to say that, oh yeah, the answers, the feasible solutions obtained are always within some fraction close to the optimal. And that's what approximation algorithms are all about. So coming up with fast algorithms that are capable of doing this. This is in contrast to broader heuristics. Question about internships. Presently, I don't, unfortunately. No, that's a good question though. If I was hosted at a university that would be something I could consider doing. But right now I'm kind of in between, kind of in a limbo state at the moment. So hopefully that's understandable. But that is a good question. Usually I'm very happy to do things with students, just generally. But yeah, no, not at this time. Definitely, I'm happy to have people on board, whether they're interested in this sort of stuff or they have questions. Like I said, I do have the Patreon, so that's one place you can always shoot things to me and ask questions about them too. Although I do them here too. But the point is that hopefully this helps with the greedy algorithm ideas here. It's a very fascinating topic. Dynamic programming. Oh yeah, I wanted to mention what I was going to say about Zero and Knapsack. One neat fact about that dynamic programming algorithm that you have in that book is that there's a way to recast that algorithm. And this is going to sound a little bit strange, especially if you've read a bit about NP completeness or NP hardness, specifically NP hardness. Presently, the best known exact algorithms we have for Zero and Knapsack, they take exponential time. This has a lot to do with some of the stuff you may know about P versus NP or things like that. So you might ask, okay, so are there ways to make that algorithm so it runs in polynomial time? And there's actually, yes, there is a way to do it. Now, you might know that if you make the knapsack capacity a constant, like if it is a constant, so that's a special case of the Zero Knapsack problem, that dynamic programming algorithm does run in polynomial time, but that's not the broader problem, right? But there is a way, based on the way that dynamic programming algorithm works, that you can resize the items to a sufficiently small enough size, because when the items are of a small enough size, you can ensure that the size of the input in relation to the size of the table is only of a certain size that keeps everything in terms of the input size still polynomial. So if you're curious about this, there's something called a fully polynomial time approximation scheme. It's a type of what we call PTAS, or polynomial time approximation scheme. And what the cool part about these is they give you a framework. Oh, you're asking about how it's exponential. Sure, let's talk about that. Actually, that's a good question. Let's talk about this. I always like talking about this with students. I know that whenever this topic comes up, it's always an interesting point to come up with, because oftentimes when we talk about running times, one very subtle detail that happens is how we measure complexity. And how do we measure complexity has everything to do with how we measure it with respect to this concept called input size, right? And very often it doesn't get enough love in CS curricula. Very often it doesn't get as much love. I know I usually drill into it a little bit. But remember, what the input size is, so if we talk about input size, in the context of the 0 and knapsack problem, this would be how much you need to you're required to represent the problem instance, right? This is normally measured in bits formally, or any other just as effective encoding scheme. So ternary, other bases like that. The only exception, theoretically speaking, is unary. Unary is the only one that if you talk to somebody about reasonable ways of what they call a reasonable encoding, unary is not one of them. There's a reason why, which I'll mention in a moment. So like binary is very common. That's normally how you often learn this stuff, is that you hear, okay, like if I have an array of length n, you know that you have n items in there, and each one is some fixed number of bits, right? So when you talk about the input size, you say, oh, it's like big O of n, or it's like n. It's a reasonable consideration of it. If you decided that the numbers were arbitrary, when you look at the running time of the algorithm itself, do those numbers pop up in the running time itself? And in this case, that actually happens with that dynamic programming algorithm. What happens here, so I just want to mention that the input size is the number of bits required to represent the instance. And the running time for this dynamic programming algorithm, so the time complexity for this one is, if for those that know big theta, if not, I'll just write it as big O for now, is n times capital W. N is the number of items. Capital W is the knapsack. Sorry, I'm getting very excited. The knapsack capacity. Now, one very important detail to notice. Now, you looked at this, you'd say, okay, that's a polynomial, right? It looks like a polynomial, right? That's what you would say when you look at this form, right? But it's not actually polynomial with respect to the input size. That's very often when we categorize like what a running time is, it's always with respect to the input size. This is a strange case because this comes up with problems that involve numbers. Is when those numbers pop up in the running time itself, let's think about it. When I give you this problem, the 0 and knapsack problem, you have a knapsack capacity. How many bits do you need to represent that? Well, it's like big O of log W, right? Or log base 2 of W. Something roughly log base 2 of W, right? So that's how many bits you need to represent the knapsack capacity. Likewise, you have your items. Each item has a profit and a weight. Each of those can be represented as a logarithmic number of bits, or for the sake of common discussion, remember those don't pop up in the running time here at all, but it's worth noting that each one of those is measured with some number of bits. It's logarithmic, right? The point is that a part of the input size is this logarithmic number of bits for the knapsack capacity. It's a number, right? So this is, so if you look at this, you see it's n, remember there's n items, so there's nothing wrong with n being here. There's nothing about that being wrong, because there's n items, so there's n times some logarithmic numbers of bits, right? That's perfectly fine. If you, just to make it easier, if you think about the RAM model, very often the RAM model, you'd think about these as like fixed sized integers, for example. So you'd have n times some constant number of bits. However, this W is not a constant. It's not a constant. It's actually measured in logarithmic number of bits. So when it pops up here, what's the proportion of a logarithmic number of bits versus just the quantity itself? Well, I'll give you a bit of a hint here. If x say if it's x, say if x is big O of log base 2 of w, how many bits, so that's how many bits it takes to represent the thing. So it's 2 to the something tells me how many, like how much this is going to be, right? So if you compare, so if you think about this, you compare w against log w, w is exponentially larger than log w, right? Because if you take this, raise this, so if you go 2 to the power of log base 2 of w, you end up with w, right? But that means it's just 2 to the power of w if you raise both to some exponent. So this is actually why this algorithm, this dynamic programming algorithm, doesn't actually run in polynomial time. It runs in it's a little bit of a strange one. This is actually one of those examples where you run into, this is technically an exponential time running time with respect to the input size. It doesn't, but it looks like a polynomial, right? It looks like one, but it isn't with respect to the input size. We give these a weird name, but these are called pseudo-polynomial time algorithms. So pseudo-polynomial because when you look at it, it looks like a polynomial, but it's only a polynomial if your encoding scheme is unary. Yeah, so this would end up being, so what I'm saying is that if you write this in the less deceptive way, this would be 2 to the power of x right here. So this would be 2 to the power of x. That's the non-deceptive way of writing it. Because that's the number of bits you need to represent that w. And that's actually what the value is, right? Because that's just w right here. Because 2 to the power of log base 2 of w is w. But yeah, no. So even though it looks like a polynomial, it actually isn't. So this is one of those strange cases where the input size actually does matter a lot when you use it in the more formal sense. For almost many applications you're going to run into where you just consider the input size the number of items you have, because for those problems, the numbers themselves don't pop up in the running time, right? In these cases, this one example, it's really weird. It's not the only one, but most certainly you'll run into a lot of these packing kind of problems that have numbers involved with them. Sometimes this comes up. But here's the neat part. You know how I was talking about how there's a way to craft that dynamic programming algorithm. So this actually is truly polynomial time with respect to the input size. The thing is, you have to make it so that this knapsack capacity is something with respect to the input size, a polynomial, not exponential. So what you do is that you gain the intuition that really, if you want it to run in polynomial time, you have to make the knapsack capacity small enough that it can be represented by one of the largest item size. Yeah, this is one of the best known algorithms for 0-1 knapsack. The exact one for using dynamic programming, yes. But here's where I'm going with this, is that if you're curious about this, there's a way to recraft this algorithm. So at the beginning of this whole approach, what you do is you rescale all of the sizes of the items. So like the sizes so that they're not too big. And you make the knapsack capacity so that it's not too big like this, because it's too big. You can come up with what we call polynomial time approximation scheme. And in this case, what you can actually come up with is an algorithm. You know how I told you that instances, like there's ways of creating instances that are like some constant times worse. If you do this and gain the intuition that actually the dynamic programming algorithm is really good at dealing with instances where the sizes of the items and the knapsack capacity are small. So if they're small, and you'll notice actually this comes up in my counterexample too. You notice that the way I was able to make really bad instances was by making the numbers in them rather big in difference with each other, right? So notice here that if I do something like this, you can actually make this run truly in polynomial time. I must stress that if you have w as a constant, So you consider a special case when W is a constant. This runs in polynomial time because that's a constant then. Broadly, it isn't. However, you can recraft this. I encourage you to look into this. It's a really fascinating topic. I can't remember if Kleinberg and Tardos has it. Most certainly, it's one of like the hallmarks of how you can use dynamic programming for an approximation algorithm. Is what you can do is you can show that if you make this change to the algorithm, and I haven't shown you that change exactly, I just told you that you rescale the size of the items and things like that. You can guarantee for any one value of epsilon. So epsilon is just some number that you can imagine being fixed, but it's any positive rational number. You can make it so that it always produces answers that are at least as good as 1 minus epsilon times the value of the optimal answer. So it means, for example, if you make epsilon, say 0.1, for example, that means that this will get you this will get you very close, within, say, 1% of the value of the optimal. So it means that even if you can't exactly solve it, there do exist polynomial time algorithms where if you wanted to have it where it gets you within 1% of the optimal answer, that does exist. Some of these problems have these, some don't. This is because 0-1 Knapsack is an example of a problem that we would call weakly NP hard. Weakly NP hard. So there's another notion called strongly NP hard. These are even in cases when the numbers in those instances for your reduction are still fixed, or no more than the size of a polynomial in the input. Okay. Yeah, no. But the big thing here is that there are ways to take the dynamic programming algorithm and bring it so that it actually is truly polynomial in this case. And indeed, as you stated, dynamic programming is wonderful for cutting down lots and lots of redundant work. Whether you take it the bottom-up approach, that's usually how I teach it, is this tabulation approach. But you can also look at it as just the combination of recursion and memoization. Some people call that top-down dynamic programming, but it's the same fundamental idea. So let's talk about. So I want to address two things. I know you have an excellent question about optimal substructure. I'll talk about that in a moment. I just want to address the part about the NP problem. So there's something I want to point out about NP. So let's talk a little bit about that, because I think it's actually relevant here, because I've used the phrase, I wanted to avoid it, but I'm going to do it because I think it's a valuable thing to talk about. Talking about what an NP problem is. So a problem that's an NP. So this I easily could spend a good hour just talking about, but just keep in mind that problems like 0-1 Knapsack aren't NP problems. They're NP optimization problems. However, they have decision counterparts where you ask, I have these items, I have this knapsack capacity. Does there exist a knapsack with a packing such that the profit is at least some value? That is a decision problem. It sits in NP. But you might ask, okay, so first, we talk about NP as a set of decision problems. Now, without needing to go into much detail, the way you frame these is just like I had with my circle with the dots in it, like the oval shape with all the dots, except each answer is either going to be yes or no. So it's always usually formed as a kind of question. So, like I said, I gave you an example just a moment ago how you can recast 0-1 Knapsack as a decision problem. The optimization version is at least as hard as that. It's at least as hard as that, because if you knew how to compute optimal knapsacks, then you can always use it to decide if an instance does have a knapsack with profit at least some value. Say K. K, whatever that might be. That's just part of the instance. So these are decision problems. Likewise, all of these problems have this property that they can be solved in polynomial time non-deterministically. One way this is characterized is through a verifier. So the idea is that imagine I was able to present to you what we call a certificate. Now I know that Kleinberg and Tardos goes into a lot of detail about this a little bit. I can't remember if they use the pure, I'm pretty sure they use the verification or witness-based characterization of this definition. There's a couple different ways you could characterize it. The most classic version is use the Turing machine, you see, because you can have a deterministic Turing machine or a non-deterministic Turing machine. That's where the non-deterministic part comes from. What this is really just is all of the decision problems that can be decided by a non-deterministic Turing machine in polynomial time, in the worst case, of course. So that's what NP actually is. And problems can be recast as things we call languages. The formal languages, they're just sets of strings. You can think of the input as bits as these sets of strings. But the point I'm getting at is that not every problem is going to be an NP, but most of the ones that you're familiar with, like decision versions of sorting, decision versions of the search problem, decision versions of the minimum spanning tree problem, decision version, they're all in NP. The NP hard problems are simply those for which there exists a polynomial time reduction from any one of these problems to that given problem. NP complete problems, those are the ones for which they have to be an NP, and meaning they are a decision problem, and they have this property. So they're NP hard and they're an NP. So as a fun little strange trademark of this is that problems that are NP hard contain the NP complete ones, but also they also include ones that simply don't even have algorithms for them. For example, the halting problem, that's a nice classic one from computability theory. There does exist a polynomial time reduction from Boolean satisfiability or even versions of 3-sat to the halting problem. And use a very classic kind of what we call a Cook reduction to do this. Now, to answer your question about optimal substructure. Now, the technique, I'm pretty sure, I can't remember if Kleinberg and Tardos uses this exact characterization, but the way very often optimal substructure is proven for dynamic programming, and I must stress that this is one element of what is called, I can't remember if Kleinberg and Tardos exactly use this phrase. I know I usually do. It's a part of what we call the principle of optimality. It's characterized by several different kinds of things, originally from like Richard Bellman's days back in the 50s, when he was telling people about all of his exciting programming, like mathematical programming work, in contrast to some of the other things he was doing, because it was hard to get funding for doing this kind of work at that time for Rand. but that's a whole other point. So principle of optimality, you might know this as has overlapping subproblems and it has optimal substructure. To prove this property holds, very common technique. I'm not sure if you've seen this one. I can't remember if Kleinberg and Tardos use this phrase. I know that I think like Corman et al. You might know it as Clorse. I think they use this phrase. It's what's called cut and paste. Where what you do is you start off with something that you think is like you presume that, hey, look, that I don't have an optimal answer. So what I do is I show you how I could take a little piece off the optimal answer and then say, hey, look, that thing, if that is also an optimal answer, then if I put it back in, the original thing that I presumed wasn't optimal has to be optimal. This is often called cut and paste, this strategy. The 0-1 Knapsack's proof for this property holding, but this is required, by the way, to show that dynamic programming solves optimally an answer. Yeah, the cut and paste argument, yeah. Yeah, so like that framework is very common for proving optimal substructure, which is a part of this, the principle of optimality. And naturally, when you have this ability to list out your instances as a recurrence relation, it implies the overlapping subproblems, right? But the point I'm getting at is that the whole idea is that you have your instance and you say, hey, look, if I can take a little piece, so I'm going to presume that I have something that is an optimal answer. Then I'm going to take a piece off of it. And then I'm going to say, that isn't an optimal answer. Just for the sake of a contradiction. Then what I do is I say, okay, I'm going to try to take this one I presumed isn't optimal. I'm going to put the thing that I took off back in and see how well it compares against what it is with that thing. So if I do that, as we would suggest, like cut and paste, what happens is you end up with a contradiction. You'll say that the answer's value, its objective value or value of that solution, is no worse. Okay, yeah, maybe I think I'm mixing the two up. Yeah, I think you're right. Yeah, I think you're right. Yeah, no. So I'm kind of in the middle between the two when I teach this. Is that I like to kind of show this technique, but I also like to use this kind of framing. But yeah, no, that's generally the technique. That's a very common technique. You might run into this very often when you run into examples like zero knapsack. Longest common subsequence is a really nice, cute example of this too. So I'll just mention that. That's another good example. Longest common subsequence. A lot of these string-based optimization problems that pop up in bioinformatics, a lot of them will have this nice kind of structure to them. Longest common subsequence, you might know this as LCS. That's another one that's a pretty good example to look at. There's a lot of examples out there for dynamic programming. But yeah, no, one neat thing about a lot of these number theoretic dynamic algorithms that have dynamic programming algorithms is if they have pseudo-polynomial running times, you can do the same trick I talked about, how you could scale the numbers. In those cases, you can bring them down to polynomial from exponential, and you can get up with an approximately good answer. But this one is a little different. Like this one, dynamic programming is your best friend. It really brings down the running time. Like this one, if you not remember, this one is where you have two strings, and I want to know the longest part. If I don't necessarily count the, I want to know the subsequence, meaning that just the two parts that match, that's the longest. On string algorithm, can you suggest? That's a good question. There's a lot of those out of there. When it comes to algorithms, there's a lot of them out there. Yeah. There's good. Yeah, there's a lot of them out there. So many that I probably couldn't name them all off the top of my head, but I could try. This longest common subsequence one for this specific problem is nice in the sense that it runs in, if the lengths of the strings are the same, then it's just quadratic. Yeah, no. When it comes to books on string algorithms, see, usually the ones I focus in on tend to be like broader books, or they're scheduling theoretic ones, because those are the kinds of problems I tend to play around with. So a lot of these packing problems, that's why I kind of picked on that example, because packing and scheduling problems tend to be my favorite ones. But that's just me picking favorites. But there's a lot of these string-based problems. I'm sure if you were to go digging around, I would have to look into it. Because I don't have as many books on just string-based algorithms. However, there's a lot of standard ones out there. Some that use certain data structures like suffix trees. There's other ones out there that use dynamic programming like this one does. But I find you'll probably find a good example, a set of examples of these. Probably if you go digging around, maybe in the bioinformatics kind of books. Not the ones that are more biologist kind of focusing. I'm talking about like books, like algorithms for bioinformatics. You probably will find plenty in those types of books, like that are just focused on string-based problems. Because many of those sequencing-based problems all are string-based problems. Yeah, no. Oh, yeah. KMP was the one I was going to suggest is a good one to know. If you're thinking about reviewing algorithms for string-based stuff, KMP, that's the one that I would probably recommend. That's my view of it. There's a lot of different algorithms, but that's one of like the standard string-based comparison kind of algorithms out there. But Like when it comes to like, hey, look, I want to know if there's a substring in this other one. That's kind of like one of the good ones to go looking at. But yeah, there's lots of problems out there like this. Yeah, no. I've met some people that do that, just that kind of stuff. But the fun part about a lot of this kind of string-based, these like maximizing the lengths and things like that, a lot of it's just combinatorial optimization. So it's always fun when I see people kind of like own it as something that's completely separate. It's like, well, all of these are just combinatorial optimization problems. So it's just another kind of object that you can study. So for example, someone like me is very fascinated about graphs and scheduling problems. So like those are the kind of problems I'm just like, yeah, let's look at that kind of stuff. But there's a lot of other kind of mathematical objects out there you can optimize over. But the beauty about a lot of these types of algorithms is kind of like the marriage between finding good data structures, but also good ideas. Very often, especially with that example like KMP, that's a good example of that over strings. Versus say like longest common subsequence, this is a good example of one where you just spoke good ideas. You see, so it's always the trouble of coming up with better ideas for new problems because there's so many new problems out there that sometimes it's really hard to know which idea you want to use. I'm getting very excited here, obviously. Sometimes you have some problem where you take one little tweak to the problem. Oh, poop. Darn. The complexity of backtracking algorithm. Okay. The big thing with backtracking is, so I'll give you a tip about backtracking. So when it comes to the time complexity here, you got to make sure you keep in mind how many nodes. So you got to remember, you got to visualize. You gotta, yeah, no, I think some years ago I read about that. That was some years ago. Like Kuss got some really fascinating stuff. It's just like a lot of stuff to take it all at once. When it comes to backtracking, the big thing is knowing how many, like if you think about it as a tree, if you visualize the backtracking as a tree, the big thing is knowing how many nodes are being exhausted and how you can guarantee that the pruning is cutting off only certain ones. Because when it comes to, say, backtracking, if you do like brute force, you know you're going to end up with something that looks like an exhaustive tree like this. Just branches out deeper and deeper and deeper, but it gets wider and wider and bushier, right? With backtracking, the big thing is observing how the pruning process reflects the number of nodes. So you got to know how much work is being done at one of the nodes in the tree versus how many there are. So just like if, for example, you're applying a recursive algorithm that does recursively calls on, say, 2 subparts, if you analyze the running time of one call, just try it with one call. So one call of that backtracking algorithm, find out what the time complexity of that is, and then figuring out how many of those are happening. Now, you have to be a bit careful about it because depending on how this algorithm works, because it's always about what the algorithm does, right? That's the one thing I always tell students is that it's so easy to just be very abrasive about how you analyze the algorithm where you just like, yeah, I'm just going to count everything. And sometimes you can overcount too many things. The point I'm getting at is that if you can do that, that's at least a good place to start, is on one call, what's the time complexity versus how many calls are actually happening. So just count up how many times that the calls are happening times how much work is happening. That's a good place to start. Now, if the backtracking algorithm does something to reduce the sizes of the instances in a very special way, you need to be careful with how much work is being done over each one of the calls. This is actually very often happens when you analyze, say, recursive algorithms that use divide and conquer, for example. Or say if you cut the instances into halves, like their sizes of how many operations you do with respect to that instance, it may cleave in half, but when you count up the total number of operations, it comes back to be the same size. A good example of this is, it's a merge sort. Merge sort is a good example of that. where you keep cleaving the sizes of the problem instances, where the amount, and I must stress that I'm not talking about like the literal encodings. I'm talking about how many operations you do with respect to that instance on that call. But in backtracking, it may make a difference because depending on what you're using backtracking for, they may be what we call output sensitive. Let me just write that down. So if your goal for the backtrack, for example, sensitive. The one thing you have to be very careful about with algorithms that exhaust things is how much space you're using. Because when you say, for example, use backtracking to exhaust all possible answers versus just trying to find one answer, that can make a big difference in the running time, because if the output gets much bigger, like it gets exponentially large, you know there's no way your algorithm's going to run anything but exponential. So just as an example of this, say for example you wanted to come up with an algorithm that generates all possible permutations of a list of n numbers. If you used backtracking to achieve this, to exhaust all the possibilities, you know for sure it's not going to run anything less than the number of permutations, right? It's just the question of how much work happens to generate each successive next object that you're generating, or next possible solution. And that has a lot to do with the calls that are happening. So like how many calls are happening versus how many leaves you end up with in that case. But backtracking, the great thing is that you like to try to prune the tree a little bit. And that's the part that is often the tricky part when you're analyzing those types of algorithms, is how is it happening? And it's always very specific. But hopefully that gives you some advice to go about it. I like to think about it like you're counting up all that work that's happening, just like when you think about divide and conquer. You may not necessarily have a recurrence relation for it or something like that, but most certainly it's the idea that you analyze the algorithm by ignoring the recursion first, and then you look at how many times that's happening. That's a good place to start, but it always depends on what the algorithm does. Hopefully that helps a little bit with the backtracking ideas. It's definitely very algorithm specific, but when it comes to the framework itself, it's about how many branches are happening versus how much pruning is happening. Because both of those things play a very intricate role with backtracking, and depending on which way you're going about it. Like if you're using an approach that's more based on just using like a depth first search approach versus a breadth first search approach. But yeah, each one has their own perks. Obviously, with backtracking, if you can try to prune off the branches using a breadth first approach. Sorry, I get very excited about this. If you take a breadth first approach, if your problem has a nice structure that allows you to prune off possible choices, because you might be able to do something about bounding it. But you can still get relatively generous bounds with big O, not necessarily big theta though. It depends also on the instances too, so you'd have to think carefully about the worst case. Hopefully that answers your question about backtracking. There's a lot you could go into with this topic. But yeah, do you have any other questions? Yeah, give that a try. Just first ignore any recursion if it's represented using recursion. If not, it might be using, say, a queue or a stack, depending on how you're traversing through the tree. Usually it's a queue. Depends largely on what you're doing. But the point is that you're doing some search space. You're exploring the search space. But yeah, so just take a look at that. Yeah, just look at what one call's doing. Figure out how many are happening. Okay. But yeah, no, sometimes it comes up pretty easy. But if you're looking for a big O, if you just straight up just allow all of the nodes to be expanded without being pruned, that might give you a big O, but it may not be necessarily tight. That's really what I'm getting at. So for example, if I'm exploring and my tree looks something like this, sorry, it's sort of melting into itself. Notice every time I have two branches, right? Every one of these I have a choice of two. So notice I start off with 1, then I have 2, then I have 4, then I have 8, and then I go 16. notice that all of this is growing. It's growing exponentially. So if I want at least a big O for this, it's probably going to be something that looks like big O of 2 to the power of n, right? But that may not be good enough, right? Depends on how tight you want your analysis to be. Okay, how to compare two algorithms in terms like microseconds. Okay. Now that's where performance really matters. So now that's where we're talking about, say, if we're doing a computer experiment, because very often there's two kind of tussles that are happening here when we talk about analysis in this sense. So very often the way I like to characterize, say when we talk about big O and all of these, we're trying to understand the efficiency of the algorithm itself. But we want to do it in a machine-independent way. If you want to do it, however, with excellent clarification. Okay, this is ripe for a computer experiment. So this is what I would recommend, because that would be something I would recommend doing with a computer experiment. So here, what you would do. So one way you could start by doing this, and this is one way I would probably start off with. I've done this before in papers. I don't do as many computer experiments with my work. I'm a very absolute kind of guy. I have like gold standard all the way. But if I do computer experiments, normally the way you'd like to do this is using like a stopwatch kind of approach. So you want to have some clock. So remember, your algorithm, the way you would go about this is you would implement the algorithm in a given programming language. And when you're doing this, you would want to make sure to document what the computer is. So you're going to have some clock mechanism. You need to know what the computer is because it's going to be computer dependent. So think about the computer that you want to run it on. So you want to ideally find a computer that best represents the machine that you would actually run this on in practice. So for example, just to give you a case, if I was trying to do an empirical evaluation of say two different algorithms and I want it for general purpose computing, like a laptop or a very basic desktop would suffice. The point is comparing the two when you're timing them. Now, in contrast, say if I developed, say, a parallel algorithm, or algorithm that runs on a parallel computer, I would ideally want to do the experiment on an actual parallel computer, like one with many cores that I have control over the cores, where I can send work to different processors to do that kind of stuff. So you would implement it for the appropriate computer. On that computer, you're going to pick a programming language, probably, that best represents what exactly you want this for. Now, this typically for papers of this kind, you'll find very commonly people implement it with all sorts of different languages, usually like your Java or C++, those types of languages, general purpose languages that are very common. Depending on what you're doing stuff with, maybe even Python, for example. Like if Python's running certain C-based scripts, might be representative. Usually in my papers, I've done it with like Java or C++, but then things are a bit different since I've done this sort of stuff. I usually recommend, if you're, say, doing this for the sake of, say, a practical measure, take a look, try to look, like maybe use like a search engine, try to find some papers that are about the topic you're interested in, and see what they use for their setups for their experiments if they're doing an empirical evaluation of them. So if you see that they're using, I'll give you a good example of what I mean. Very often the types of problems that I study, there's also like a parallel literature, like another literature just sitting out there that all they do is they use solvers. So very often people would use, say, like a C++ or a Java, and then you'd use a certain package with it. Like, for example, Cplex, or an open source version of this. So, for example, if I was doing stuff with like linear programming or integer programming and stuff like that, the person might use Cplex to generate the solutions of the instances, but they may use this also as kind of like a benchmark because they want to know, does my algorithm perform better than the solver does? But that's a whole other point in itself. But yeah, no, C++ is a good choice. There's a lot of languages out there, but most certainly C++ has a lot of packages. and libraries that might accompany things. I know, for example, when I did a lot of my parallel stuff back some years ago, I usually used, I think I used C++, and then I used, I'm tempted to say, I think it's OpenMP. That's it. It was OpenMP. I think I used for that. There's other ones out there too, but I think I used OpenMP because that evaluation was for a shared shared parallel architecture where you have shared memory. But yeah, so anyways, you have the setup. You need to have some idea, so make sure you document like what your computer specs are. Tell them what programming language you implemented in. If you're doing a specific experiment, maybe even giving them the source code is a good idea. Maybe put in the appendix, or there's some place you can find it, like say on a GitHub. Give a link to that maybe. Then in the given programming language you're interested in, you want to look into what timing functions exist. So very often the way this works for a lot of these libraries or function calls is that you call it the first time, it gives you a time. Then, when you're done calling the function for your algorithm implementation, your program, you press you make the time call happen again, and then you take a look at the difference, how much time occurred. So you see how much time elapsed. You collect up all of these for a whole set of instances. So what you'd basically do is go through maybe a nested loop. Or, for example, you build a table or an array that stores this information, like the timing results of how much time it took. And then you could take this and maybe save it to a Word file. Sorry, not a Word file, a text file. For some reason I'm thinking Word. I'm like, what am I talking about? Save it to a text file or some spreadsheet, depending on how elaborate you want to get with this stuff. A text file, usually I use comma separated value kind of file, like a CSV. Just make it so it writes all the data that you have from each one of the experiments you did. And make sure, of course, run it on a few of them to make sure that, like, try running it several times to make sure you're not getting any strange stuff happening. But the big thing is make sure you get these timings. Different programming languages will have their different setups for these, but generally the idea is that you call it to make it so it starts. So you have a current time, and then you call it again to get a second time. That'll give you two different numbers. You take the difference of the two to tell you how many in some unit. Make sure you take a look at what that is. And then you can plot these out. So you do this for one algorithm that you're interested in, like say the claim is that it's an improved algorithm. You do it for that one, and then you implement the competing one, or another one, or maybe one or two other ones, just to see. And make sure, of course, when you do this, you have to do it very carefully. So make sure you carefully check those implementations. And then you time those two, and then you can plot them all out and see how they differ in terms of performance. That's a very common way of going about this experimentally. So if you want to go and say, hey, look, this one performed better than this one for this size of instances. Now, I didn't get into the instances yet, though. That's another part of the experiment. It always highly depends on the instances of your problem, so the one that you're looking at. So oftentimes you want to find, it largely depends on your interest. Do you want to come up with the claim to say that this is good for an average instance, like instances that are just things you might run into in practice? Or are they going to be ones that are always going to be like the benchmarks, like the really hard ones? Very often, if you're interested in like stress testing your algorithms, you might want to look for your worst case instances for the given, for your given algorithm. So you would try to find or identify these. If you're just doing a random sampling, make sure you try it with a few different samples to see what you can do with those. Make sure you have a large number of instances. Try them for as large of sizes that you can. Sometimes they might take a while. I remember one of my first papers was on combinatorial generation. So some of the stuff that we talked about just a moment ago, like enumerating combinatorial objects, like one of my first papers actually was on generating what are called integer compositions. So these are just a finite sequence of numbers. And I want to know, for example, like if they add up to a number, like 10 or something. So for example, 2 plus 2 plus 2 plus 2 plus 2, that's 5 2s. That's 10. I want to know all the ways to sum up to 10 using positive integers and the possibility of using a 0. It's what we call weak integer composition. So I had a paper some years back. I think it was like 10 years ago at least, something like that. So 10 years ago I worked on that. It was a good time. It was my first paper. Do I look back on it and be like, well, some of the stuff I do now is a little bit more interesting, but that was my first one. It was published in a journal that's meant for like algorithms and operations research, because sometimes like chemists and things like that, they need sometimes these kind of objects. I know I've seen some pretty interesting kind of applications that come out of these kind of things. When it comes to internships, it depends largely on what you're interested in. And I don't have any direct connections right now to given universities, though I know some people that may be interested. It depends largely on what you're interested in and what you mean for the internship. Like if you're looking for like summer research, or you're looking for like job prospects, like those are different things. But most certainly, I'm not the greatest to come to for this. Like I said, I'm somewhat in a limbo position. Right now I'm kind of in a position where like I'm not quite at one institution, so I don't have too many direct contacts. However, these are things where you look for the person that maybe you're interested in working with. Like, for example, I'm usually quite happy to work with people, but it's the question of money when it comes to an internship, and I don't really have that at the moment. Just to be honest with you. But yeah, no. When it comes to answering question, I don't have direct internship connections right now, at least from an institution. But usually I recommend, if there's somebody that you're interested in working with, reach out to them. Maybe send them an email. You can send me an email. I mean, it's one of those kind of things. But when it comes to this sort of stuff, I don't really have any openings or anything for internships, because right now I'm sort of, like I said earlier, I'm in a limbo position where I'm not quite in one institution or another one. I'm kind of independent at the moment. But I do appreciate the question. One thing I can recommend is look into companies that are always looking for people. A lot of those connections you can find through universities sometimes, or colleges. I'm pretty far removed from that kind of stuff, but because I'm a theoretical computer scientist through and through. it's kind of what I do. But yeah, no, excellent questions. But yeah, no, this is what I would recommend as a good startup for doing an experiment. I know I've done things like this in the past. So if you find yourself looking for like any more advice on that, just shoot me an email. I have a couple different emails. If you're asking me questions about research related stuff, my research email I usually use for research stuff or personal stuff is drpage at pagewizardgames.com. If you email me at this, I could give you more advice on this if you're interested in. Like, I have already told you basically everything here. But you might find that email helpful if you have any other questions. But generally, if you're looking for much more specific advice, like when it comes to like content or notes and stuff, Patreon is the best route to go with me. I have patreon.com/pagewizard. But yeah, anyways, hopefully that answers your questions. Those are good questions. But yeah, I don't have too many of those kind of opportunities. But well, certainly I'm happy to help in any way I can. Okay. So I was thinking what I'm going to do now is I'm going to talk a bit about this so-called cut property in a spanning tree. So let's move into talking a little bit about that. And I think we're going to call it a day here today. I think we had a lot of really interesting questions. So let me just going to get the chat off the screen here. I just had to get some water here. There we go. But yeah, if you're enjoying this, make sure to subscribe. Tell your friends to come on out. We have ourselves a good time here. I do live lectures like this every week. And I also do an entertaining show, like usually like on Thursdays. Right now it's just Tuesdays and Thursdays I do things live. But if I can get more people on board, I might do more. But I do YouTube videos almost every day of the week. Like at least during the week. But yeah. So let me just get the let's start on the kind of this big part. And no worries, no, have yourself a beautiful night there. It's a pleasure to come and hanging on out. I love answering these kind of questions. And good luck, of course, going through Kleinberg and Tardos. It's a good book. It's a lot of work. It's a lot of work. That one I know. So, yeah, no, you have yourself a beautiful night there. And I'm going to get into talking about minimum spanning trees. So I'm going to get on that. And let's get started on here. Okay. So I want to talk a little bit about minimum spanning tree. Oh, yeah, no, if you got to get going, get some rest, okay? That's one piece of advice I can give students, given that I've done this and I used to be a student myself, is, yeah, getting a good rest. Even when you tell yourself you're going to get a good rest, it's always the fun of convincing yourself to get into bed earlier. It's always the tricky part, because you can always tell yourself, oh, I'm going to make sure I get lots of rest. Then by that time you look at the time, you're like, oh man, no. Yeah, no worries. No, thanks for coming on out. Now have yourself a beautiful, I guess a beautiful sleep. Yeah, no, it's always some of the fun of all this stuff. Okay, so let's get into talking a little bit about the minimum spanning tree problem. So I want to remind you of what that is. Then we're going to talk a little bit about this thing called the cut property. And then, of course, I'm going to prove that for you. And, of course, after I'm going to show you a couple of applications of the cut property. I'll see you later. So I'm just going to give you a quick reminder, just for anybody that's here, just what the minimum spanning tree problem is. And then we're going to talk about how we could solve that problem. Now, I'm not going to go into terrible details here. However, I do plan in the future to talk more about the algorithms I will outline here. Okay, so just as a reminder from last time, we have the minimum spanning tree problem. So I'm going to abbreviate minimum spanning tree as MST. So given a connected undirected graph. I must stress that I'm presuming the graph is simple, but it doesn't matter much with this algorithm. There's ways to modify it so it works with multigraphs. I think I talked about that at one point in one of my previous lessons, but if I have a little bit of time, I'll talk about it. So given a connected undirected graph G is equal to VE, where V is the set of vertices and E is the set of edges, I want to compute a spanning tree with a minimum total cost. That means the sum of the edge weights. So I want to compute a spanning tree. Now remember, a spanning tree consists of all of those vertices in the input graph. So the tree has to contain all of the vertices in the graph. And it also has to be a tree, right? But it's not just any old spanning tree, because we can use depth first search or breadth first search to compute such a spanning tree. As we proved in a previous lesson, we showed that the forward or discovery edges in an undirected graph guarantee such a spanning tree. So we want one with the best cost, okay? So let's just see an example here, just to make sure to remind everybody about this. So let's do an example. It's going to be a different example than the one I have in my notes. I must stress that the notes are going to be available on patreon.com/pagewizard. So if you're looking for the resources for this, they'll be available there. So imagine I have A, B, F, D, E, and C. Now let's look at the weights. So I'm just going to make this a little easier for us to see. Let's make them 1, 1. I'm just going to make it a little easier for you to see where the minimum spanning tree would be. And let's make this 3, 2, 10, 8, and 6. I think I got all the edge weights. Yeah, I've got a 1 here. Let me just put the 1 here. So you'll notice that I deliberately put a path from A over to B of just ones. This is an example of a spanning tree. So the spanning tree in this case consists of these edges. But it does not have to be a path, just to be very clear. A tree doesn't have to be a path. It just has no cycles, right? So there's an example of a minimum spanning tree. The total cost of this tree is 1 plus 1 plus 1 plus 1 plus 1. So there's how many ones? There's 5 of them. So I must stress that that's because we're adding the edge weights. So if this, for example, was a 2, that was a 2, that was a 2, that was a 2, that was a 2, that's 10. Just as an example. So that's the minimum spanning tree problem. So remember, we want to compute the minimum spanning tree. So this is what we call a minimum spanning tree. Okay, so what I'm going to do is I'm going to be focusing in on what exactly, or how exactly, to be a bit more precise, how do we compute one of these? So in algorithm design, very often what we'd like to do is come up and try to characterize the problem based on some special property it has that tells us how to compute what we're seeking. So in this case, I would like to know something about what a minimum spanning tree looks like in such a graph, in a weighted, let me throw that in there too, a connected, weighted, undirected graph. There's a lot of prefixes here, okay? So what I want to do is talk about how we could characterize such a thing. Now there's all of this has to problem. So this isn't going to be some magic thing where every time you have a problem, there's some way of characterizing it so that there's a nice, easy way to tell me how to build the answer. That isn't going to be true for every problem. In fact, there's some problems out there that don't even have algorithms that solve them. This case, we're going to have a really nice characterization for how we can obtain a minimum spanning tree. In particular, it's going to give us the key ingredient for how to find an edge in a minimum spanning tree. So the way I'm going to characterize this is by giving you something we're going to call the cut property. And we're going to prove this property, and I'm going to give you a couple of applications of how you can develop algorithms using this cut property, okay? So I'm going to state it as a theorem. So a theorem. So it's going to be called the cut property. You're going to see why I call it that, or why it's called that. And I must stress it's going to be a little bit wordy, so please bear with me, okay? So consider any weighted, and I must stress whenever I talk about the graphs in this context, it's always an undirected, simple graph. So consider any weighted connected graph G is equal to V, where V1 and V2, these are two subscripts, are two non-empty sets containing the vertices of V. So it means all the vertices, they're going to be in V1 or V2 with no common vertices. Now, for those that are acquainted with set theory, what I've described to you is that V1 and V2, these two disjoint sets, they have no elements in common. These two sets partition the set of vertices, V. That means that all the vertices are going to be in one of these two buckets, V1 or V2, but it can't be in both. So for example, V1 could be, say, these vertices here, A, B, and F. And V2 can consist of D, E, and C. Notice I've included every vertex in one of the two buckets. Now, let edge E, whose endpoints are going to be U and V, be some edge in G with least weight, where U is in V1, so it's one of the ones in this first, like in the first set, the first bucket, in V1, and V is in V2. Here's the big thing that this cut property is all about. It says that there is a minimum spanning tree T that contains E. So do you notice that in my instance here, I have exactly one minimum spanning tree. There's only one possible one here. Now, I want to show you how this cut property could be used after we go through the proof, but I just want to give you an example of what I mean by this. So here's an example. I gave you V1 is A, B, and F. V2 is D, E, and C. What the cut property is saying is if you give me a least weight edge, so an edge with the smallest possible weight among those where U is one of these vertices, the ones in V1, and V is the other endpoint of the edge that's sitting outside of it. We call these cut edges. These cross the cut. So that's where the name comes from. So, for example, let me show you what these edges, which edges these are. So there's one edge right here, right? There's that edge. There's this edge. There's this edge. And there's this edge, right? So I think I got all the edges. So those are all the edges for which there is, so it's that one of the endpoints is in V1, the other one's in V2. So those are all the possible, what we call cut edges. So what this cut property says is if you pick the one with least weight, so notice this one has weight 1, that has weight 1, that has weight 1, this one has weight 1. This example is not terribly interesting, but the point is notice every single one of them. Doesn't matter which one it is, if I pick the one with least weight, it's in some minimum spanning tree, right? So, for example, notice that this one has least weight. Notice it's a part of the minimum spanning tree. So that's what the cut property says. It doesn't say that all the cut edges are. This is just one example where all the cut edges are part of a minimum spanning tree. But it's not all of them always. This is just an example where any one of these could be edge E in this statement. So this is very often the key ingredient for developing and discovering or designing algorithms for the minimum spanning tree problem. So let's prove this cut property. So here we go. So let's write out a proof. Now, you might ask, Dan, what exactly is the game plan here? Because I always like to go into a game plan about what exactly we're going to try to do. So I want to give you a flavor for this first before we get too into all of this. So the first thing is I want you to think in the recesses of your mind about trees, properties that trees have. Remember, a spanning tree is a tree, right? It means that there's a lot of equivalent definitions for a tree. Likewise, they have properties for which that are very helpful for us. For example, if I add an edge into a tree, then it creates at least one cycle, right? Likewise, if I remove an edge from a tree, it creates two new connected components. So these are two examples of properties that are going to be very helpful for us for proving this claim. So what I'm going to do is I'm going to start off by just simply saying, hey, look, I'm going to start off with a minimum spanning tree. Then what I'm going to do is I'm going to show you that the edge E that I have in the cut property statement has to be in this tree. So if I presume that I have a minimum spanning tree, I'm going to show you that by including E, I still end up with a minimum spanning tree. So it doesn't matter if I presume it is a minimum spanning tree, and the resulting one will have edge E in it. Okay, so I'm going to give you a recipe for how to create a minimum spanning tree given the fact that you know one exists. So if you have one, I'm going to show you how you can put edge E in as per this statement. So let T be a minimum spanning tree of G. So we're going to start off. So T is going to be a minimum spanning tree. Now remember, it is a tree, right? So by the equivalent definitions of a tree, so I'm going to use the fact it's a tree. I'm going to use one of the two properties I just talked about. Because remember, if T has E in it, we're done, right? We don't have to do anything. However, if it doesn't, as we need to really show here, if T does not contain E, then its addition to T creates what? What does it create? What does it create? It creates a cycle, right? We've added one new edge into a tree. It's connected, so we're going to add in one more edge. It's going to create at least one cycle. Creates a cycle C. So now we have a cycle. So I'm going to give this new modified graph that I've just created a name. Let now T prime be T plus edge E. Now remember, T was a spanning tree, right? Because it's an MST, right? So T was a spanning tree. Then its addition then I got something more interesting to say here. Let's do that. So I'm going to draw a little picture over here to give us some intuition what's going on here. So remember, I have a cycle. So I'm going to draw us a little picture to help us kind of get an intuition around what's going on here. So anyways, imagine I have just my graph. I've got something going on with this graph. I don't know. It doesn't really matter a whole lot what's going on here. This is just some part of the graph. And this is another part of the graph. The point I'm getting at is just some part of the graph. It doesn't really matter what I'm drawing inside of here. Now, there's going to be vertices. There's going to be vertices. The vertices in this part of the graph are in V1. And the vertices in this part of the graph, including this one here, are in V2. Now remember, edge E, by definition, looks like this, right? So this is E right here. So I've included edge E into my MST, right? Now remember, this is just an edge in the graph. Now remember, it is a spanning tree, right? So there had to have been some way of getting it so that U and V are indeed a part of the spanning tree, right? So there had to be some way to get to them, right? So naturally, there's going to be some other edges. Now, I must stress that it's very easy to look at this picture and say, Dan, what the heck is going on? Why are there all these other things going on? Remember, I'm going to focus in on the edges that cross this cut. Remember, notice this is a cut, as we talked about earlier. So these edges here, suppose that these are edges in the minimum spanning tree. Suppose that these are in the minimum spanning tree. Because of the way we've constructed this right here, there had to have been some path, because remember, a tree has unique paths that go from one vertex to another, right? So that means that there has to be a path from U to V, but not using E in T. So that means that there's going to be some pathway that gets me back here. Then when I put edge E in, then I get a cycle. That's my cycle C. What my claim is that there's this edge that's a part of the minimum spanning tree. Suppose that's F. I'm going to give that a name. And let's see what happens now. So remember, the big thing you need to remember is that edge E has least weight across this cut. All these are cut edges, right? So let's talk about this. So T was a spanning tree, so right? So T was a spanning tree. So in T prime, remember that's what we got over there, that weird concoction where we've added E in and we got a cycle now. So in T prime, there is some edge F, which is going to have endpoints U prime, V prime, along cycle C, where it also has one endpoint in V1 and the other in V2. Now remember, because E has least weight, right? Since E has least weight, what can we say about E and F for their weight? What can I say? Well, remember, E is not equal to F. They're not the same edge. These are two different edges. What can I say about the weight of E versus the weight of F? Almost certainly F's weight can't be less than E's because it's the least weight edge across this cut, right? So we know F is not equal to E, but that means that the weight of edge E is no more than the weight of F. So the weight of E is less than or equal to the weight of F. Now, here's the neat part, because it is we originally had a spanning tree, right? And now, if I were to get rid of F, this would break the cycle, because it's across the same cut. At least that's one way you could think about this. If one removes edge f from T prime, then T prime is a spanning tree. The spanning tree and its total weight is no more than with T. So the total cost doesn't, it's either gotten better or it's the same, right? So just remember, the reason why when I remove F, so this is the primary reason, is that, remember how I said earlier that if you take an edge, because remember, T was a spanning tree, right? So when I remove this edge, it breaks the tree into two smaller trees, right? But now I have this edge E that bridges the pathway that would have otherwise not existed in T. So now I still have a spanning tree as opposed to two smaller trees. So that's why. So let's see here. So what does this mean then? It means that we still have a minimum spanning tree. Is that fun? That's pretty exciting. So why? Because T was a minimum spanning tree. Therefore, sorry, it's sort of melting. Therefore, the resulting tree, T prime, is also a minimum spanning tree. And that completes the proof. So notice that all I did was I showed you the recipe for how to make a minimum spanning tree with the edge E in it. So you might ask, Dan, well, how exactly do we use this cut property to come up with algorithms to solve the minimum spanning tree problem? Let's talk about that. So the first thing is I want to remind you what the cut property is. So let's go back over here. I just want to remind you of how this works. Okay, so remember, the cut property states that if I take and I partition the vertices into two disjoint sets, V1 and V2, that means that V1 and V2 are like two buckets. I put all the vertices into two buckets. So what it's saying is, if I pick off an edge where one of the endpoints is in V1 and the other one is at V2, what I'm saying is it's such an edge with least weight, it has to be a part of some minimum spanning tree. So this gives us a recipe for how we can pick our edges such that we end up with a minimum spanning tree. That's at least how we would like to use it. So I'm going to mention you a couple of different ways we can do this. So one way we could do this, and I'm going to this one I usually spend more time talking about. I may in another video, or in another lesson I may talk about this, is that one very natural way to do this is you start off by putting, just look at our example here. Suppose that you have, and I must stress, remember, we can't just use one example to prove the correctness of an algorithm, as we previously discussed. So suppose that I start off with V1 being one of the vertices, and then everything else is in V2. What does the cut property tell us? It tells us if we find the least weight edge that crosses this cut, that it is a minimum spanning tree. It's part of some minimum spanning tree, right? It extends it into another one. So for example, notice that this is a least weight edge. So what I can do is I can extend and grow the tree from this one seed. I like to think of it like a seed. And I end up with this edge. And we know that's a part of some minimum spanning tree, right? We could continue this process. So for example, I can just look for the least weight edge here. We'll notice there's 1 versus an 8 here. Well, notice that, well, means I should include this one. But look, that's part of the minimum spanning tree, right? But notice I'm growing V1 by consuming more and more of the graph, like a blob. I like to think of it like a blob that starts off over at the source or start vertex, and I must stress it doesn't matter which one you start at. The same principle applies of the cut property, right? The cut is always it's always the edges that go from V1 to V2, and we always pick the least weight edge that comes from V1 to V2. And that is always going to be closest to the blob, which happens to be consuming all of the vertices that we have so far, right? So it's closest to the blob. So notice which one of these vertices is closest to this blob? Well, it's E, right? Just 1 right there. So it's like 1 versus 10 versus, let's see, we've got a 3 there. But keep in mind, we might have to have some mechanism to keep track of which ones are the smallest values for how close they are to the blob. And this idea, you can keep repeatedly doing this. I'll encourage you to do that. This is one way of applying the cut property, and this gives you what we call Prim's algorithm, or the algorithm of Prim and Jarnik. So this is how you get Prim's algorithm. You start off with an initial seed, and you grow a minimum spanning tree from that seed by always picking a least weight edge that crosses the cut from V1 to V2, where you start off with V1 at 1 vertex. And when you're done this process, then you have a minimum spanning tree, because by definition, you've always picked the least weight edge every single time, and you can just keep using this over and over again. It's a very natural application of the cut property. So the Prim's algorithm is just simply where you grow a minimum spanning tree from a seed. So the way the cut works here is that you always pick the least weight edge from one side of this cut to the other, or from inside the blob to the outside of the blob. Think of it as picking the closest vertex to the blob. That blob is just really hungry, man. Now, there's another way we can use this cut property. This is at least another way, and this is how you can come up with another algorithm. This one's a little bit trickier, so I want to show you where this cut comes from. So let's go through the same kind of process as before. Now, you'll notice that the way I always am maintaining this blob in Prim's algorithm, keep in mind I haven't given you the formal description of what Prim is. I just gave you how it works and a way to convince yourself of its correctness. You might ask, okay, so that seems rather natural for the cut property. Like, just because the cut is rather blatant for where it comes from. How exactly do you make sure you end up with a minimum spanning tree at the end? Well, one, the cut property tells me it's going to be all the edges I pick are part of some minimum spanning tree, right? The other thing is, notice I'm never creating a cycle. Do you see that when I do this, whenever I pick an edge that crosses the cut, I'm not picking an edge that's going to go back into the cut, like onto the opposing side, right? It always goes from inside to outside. It doesn't go inside to inside. So you know you're not going to end up with a cycle. So you'll notice that another way you can think about picking this least weight edge is just to globally pick the least weight edge. Does everybody see that? So for example, I could just pick this edge and say, hey, look, that edge should belong to some minimum spanning tree, right? It's the least weight of all of the edges. That's one thing you might say first up. However, you might say, okay, well, if I keep doing this, like suppose that this had an edge weight of 1, you might be compelled to pick that one, and then this one, and then this one. And you end up with a cycle. We need some mechanism to just prevent us from creating a cycle. Prim's had a very natural one for how the way the cut works and how you pick the edge that always crosses the cut, right? Why don't we try to use that idea here? So I'm going to augment this with another idea, where what we're going to do is, instead of having one seed, we're going to have seeds at every single one of the vertices. So they're each going to be what I'm going to refer to as a cluster. So this idea is going to be what we call Kruskal's algorithm. So Kruskal's algorithm goes into more detail about this, but I want to show you how the cut property comes, like it's used here to ensure correctness. So what you do is you start off with all of these clusters. So I like to think of this as growing minimum spanning trees from seeds in clusters. So you can think of each cluster as its own separate little connected component with respect to the subgraph on that what we would call the induced subgraph of those within the cluster. So what's going to happen is inside of each one of these, a minimum spanning tree is going to grow. And when we add enough edges, we end up with a minimum spanning tree. So we have a whole bunch of these smaller trees of least cost all within each one of these clusters. When we're done, we're going to keep merging these clusters together to end up with one big tree. Think of it like bubbles. Each one of these is going to have a little minimum spanning tree for itself in there. Now, there's two problems. One, I need to make sure there's no cycles. So what I'm going to do is I'm going to use the same idea I just talked about. I'm only going to add an edge that crosses from one of these clusters to another cluster, never to the same cluster within itself. Same idea. So very often when you actually think about this, what we're actually trying to do is we're trying to make sure that we never pick an edge where they belong to the same cluster. The data structure you can use to maintain this is what we call disjoint set data structure, or some people call union find data structure. I'm not going to talk so much about that here right now, but that is the key ingredient to maintain these clusters. The other one is naturally always picking a least weight edge, such that you always make that edge so you add it to part of your tree to merge two clusters together. You use sorting. So all you're going to do is you'd sort edges, least to most. So ascending order by weight. Then you add least weight. Add next least weight edge between two clusters to merge them. So that's how this is going to work. You sort first the edges. Now, I'm not going to go into too much detail about how specifically that is done here. I mostly want to talk about the cut property. So notice that if I pick a least weight edge, and the edge goes from one cluster to another cluster, which we maintain with these disjoint sets, whenever I pick the next least weight edge, if it crosses from one cluster to another, we can guarantee there's no cycle, right? So, for example, if I include this one, what I can do is I can pick this one, and then I merge these two, right? Likewise, I pick the next least weight edge. Well, notice that I have a 1 here. So far we're doing okay. This is a pretty nice simple instance. So I could include this one. Notice I go from inside to another cluster, never within itself, okay? So you can keep doing this process over and over again by merging the clusters. So now notice that I only have 1, 2, 3, 4 clusters left. So notice that when I'm done, I've added enough edges such that it's only one big cluster. And inside that cluster is going to be a minimum spanning tree. Now, you might ask, Dan, how do you know it's a minimum spanning tree? Now, you can prove this with mathematical induction, but the key ingredient is how you pick the cut. So the cut is a little bit more subtle here. So notice here that when I picked and merged these two clusters into one and picked this edge, well, notice here, I did that because I had least weight and there were two separate clusters, right? There are two separate ones. Well, think about it. Let's consider the next edge we'd put in here. Well, we have one cluster here of vertices. And whenever we add a least weight edge, it is the next least weight edge. It goes from one cluster to some other cluster. So what's the one cluster we currently have? You have these three vertices. What if this is V1? It doesn't matter if this is V1 or V2. It's just one of the two. And everything else outside of this cluster is V2. So everything else is out here is V2. How do I merge two clusters? I always pick a least weight edge. Specifically, the least weight edge that separates one cluster from another, right? And that's actually how you pick the cut. So this is actually the cut property put into the setting of Kruskal's algorithm. This is the key idea that makes Kruskal's algorithm correct. Is that whenever I pick the cut, it's always going to be the one that merges to the clusters. And one of the clusters, it matters, the cut is going to be from one cluster to some other cluster, okay? So that's how you can use or see how the cut property pops up in two different algorithms that are commonly used to solve the minimum spanning tree problem. In fact, if you keep repeatedly doing this process, just like I did with Prim, you'd end up with a minimum spanning tree. I'm not going to prove that formally here for you, but I hope you could see how fascinating some little property like this can be. So that's everything I have to say about that. So I'll say thank you so much and have yourself a beautiful day. But anyways, sorry, I got into my autopilot mode. I'm having a little bit of fun here. So that's the cut property. I thought I would show you this because last time I felt I didn't cover it deep enough that I felt it was done in a way that I feel is proper. I thought it was okay what I did, but it definitely was not good enough for me. So I wanted to go through this more carefully in case you had any questions. So are there any questions out there about the cut property? But yeah, the big thing is the way this cut forms, and we pick the least weight edge that crosses the cut. In Prim's, it's quite literally just this, right? Except we just start off with one vertex, then we expand it out. In Kruskal's, the cut is always going to be from one cluster to some other cluster. But the cut is going to be everything else outside of that one cluster. But yeah, no. Are there any last questions before we stop for today? It seems rather quiet. I don't think there's any questions. Let me get the chat open here. But yeah, no, if there aren't any other questions, I think I'm going to head on out for today. I want to say thank you so much for coming on out. It was a pleasure. And I really appreciate a lot of the questions we had earlier on in the session. So that being said, if you enjoy what you've seen, make sure you tell your friends to come on out. I'm sort of like Santa Claus. I know these things. Also, if you want to get the notes from today's session on the cut property, be sure to consider supporting on patreon.com/pagewizard. So I have a Patreon page over there where I deploy the notes. And currently, I have a couple quick announcements. I'm currently working on the website so that I can try to make it so that all these resources are more hosted on my website, which is currently under construction. So I'm currently working on that along with some other fun projects around the website. I'm also going to be working on a mailing list so that way you have an easy link that you can share with friends to keep up with updates on what's going on here. I have a lot of busy things that I'm doing here, and I hope you appreciate a lot of the projects that are coming out. I know I'm very excited. So I want to say thank you so much, everybody, and have a beautiful day. I'll see you later.